What is a theoretical physics? Theoretical physicists use mathematics to describe certain aspects of nature. So Isaac Newton was the first theoretical physicist, although in his own time his profession was called natural philosophy. By Newton's era, people have already used algebra and geometry to build marvelous work of architecture, including the great cathedral of Europe. In order to describe things that are moving or changing in some way, Newton invented the calculus. The most puzzling and intriguing moving things are visible or available to the humans have always been the sun, the moon, the planet, and the star we can see in the night sky. Newton's new calculus, combined with the laws of motion, made a theoretical mathematical model for the force of gravity that not only described the observed motions of planet and star in night sky, but also of swinging weight and flying cannonball in England. Today, the function of theory and observation are divided into two distinct communities in physics. Both experiments and theories are much more complex than that back in Newton's time. Theorists are exploring natures of nature in mathematics that technology so far does not allow us to observe in an experiment. Many of the theoretical physicists who are alive today may not live to see how the real nature compare with a mathematical description in their work. Today, the theorist has to learn to live with ambiguity and certainty in their mission to describe nature using maths. The story so far. In the 18th and 19th century, Newton's mathematical description of motion using calculus and his model for gravitational force were extended very successfully to the emerging science and technology electromagnetism. Calculus involved into classical field theory. One magnetic field were thoroughly described using mathematics. Many physicists felt that the field was finished, but there was nothing left to describe or explain. Then the electron was discovered and the particle physics was born. Through the mathematics of quantum mechanics and experimental observation, it was deduced that all non Then the electrons was discovered and the particle physics was born. Through the mathematics of quantum mechanics and experimental observation, it was deduced that all known particles fell into two. One is known as a boson and the other fermions. Bosons are particles that transmit force. Many bosons can occupy the same state at the same time. This is not true for fermions. Only one fermion can occupy a given state at a given time, and this is why fermions are particles that make a matter. This is why solid cannot pass through one another. While particle physics were developed with quantum mechanics, increasing observational evidence indicated that light as electromagnetic radiation traveled one fixed direction. This discovery and the mathematics that Einstein developed to describe it and the model it in a special theory of relativity, when combined with the later development of quantum mechanics, gave birth to the rich subject of relativity quantum field theory. Has had many observational success that proved its worth as a description of nature, but two of the predictions of this nature have staggered the public and the scientific imagination: the expanding universe and the black hole. Both have been observed, and both encapsulate issues that, at least in the mathematics, brush up against the very nature of relativity and the existence. Why did string enter the story? Relativistic quantum theory have worked very well. However, the theory itself only works when we pretend the universe is purely classical and that quantum mechanics is not needed in our description of nature. String theory is believed to close this gap. Originally, string theory was proposed as an extension for the observed relationship between mass and spin for certain particles called hadron, which include the proton and neutron. Things don't work out through, and the quantum chromodynamic eventually but the particle in the string theory arise as excitation of string, and included in the excitation of a string in string theory is a particle with a zero mass and 2 units of spin. If there were a good quantum theory of gravity, then the particle that would carry the gravitational force would have 0 mass and 2 units of spin. This has been known by the gravitational physicists for a long time. This don't mean that the string theory is not without its deficiency, but the zero distance behavior is such as that we can compare quantum mechanics and gravity, and we can work or talk sensibly about a string excitation that carry the gravitational force. This was very great hurdle that was overcome by the late 20th century physicist. So what is a string theory then? Think of a guitar that has been tuned by stretching the string under the tension across the guitar. Depending on how much string is plucked and how much tension is in the string, different musical notes will be created by the string. This musical note would be called or set as excitation mode of the guitar. In a similar manner, in string theory, the element particle we observe and particle accelerator would be brought off as the musical note or excitation mode of the elementary string. In string theory, as in guitar playing, the string must be stretched under the tension in order to become excited. However, the string in string theory are floating in time space. String theory are classified according to whether or not the strings are required to be closed loop and whether or not the particle spectrum includes fermions. In order to include fermions in string theory, there must be special kind of symmetry called supersymmetry, which is the means for every boson, and there is corresponding fermion. So the symmetric relate the particle that transmit force to the particle that make up the matter. And this surprising relation about the string theory are not just theories of one-dimensional object. There are higher dimensional objects in the string theory with dimension from 0 to 9 called p brand. In terms of brand, what we usually call a membrane would be 2 brand, or a string is called a 1 brand, and a point is called a 0 brand. What makes a p brand? A p brand is a time object that is a solution to the instance equation in the low energy limit of superstring with this energy density of non-gravitational field confined to some p-dimensional subspace of the 9 space dimension in theory. For example, in the solution with the electric charge, if the energy density in the electromagnetic wave disturbed along the one-dimensional line would be considered as a p brand with p equal to 1.